first 3-4 minutes or so in just giving a summary again of what I did in the first lecture. That's 2 days ago, and many of you will have forgotten what I said. And then I want to apply all this today and discuss examples, classifications, and present some open problems where I really would like to see the solutions. Okay? So also the little bit of revision gives me an opportunity to fix the notation again. So the setup was M bar is an n-dimensional Kaehler manifold. Okay. And M is a real hypersurface. So real codimension is 1. And I assumed this is connected and orientable so that we have a global unit normal field. And then we have the Kaehler structure induces on the hypersurface this so-called almost contact metric structure. So phi is basically the tangential part of J, the complex structure on the Kaehler manifold. Xi is J of the normal vector with a minus in front of it, eta the metric dual one form of Xi, and G the induced metric. And what was also what we needed is the fundamental 2 form, which is defined by G of phi x y. And we've seen that this is always closed 2 form. And the definition, so we were discussing contact hypersurfaces, and M is called a contact hypersurface precisely if there exists a smooth and everywhere non-zero function rho on M such that d eta is 2 times rho times the fundamental 2 form omega. And we saw that this condition, so the last condition, if one works out explicitly d eta, one can rephrase this in terms of a condition on the shape operator and the tensor field phi, namely that a phi plus phi a is equal to 2 rho or phi. That's an equivalent characterization for contact hypersurfaces. So and then we had a couple of properties of contact. So if M is contact hypersurface and n is greater or equal than 3, so then we had a couple of properties. The first one is that M is always a Hopf hypersurfaces, which means that that Xi is a principal curvature vector. Another condition we had is, which is very useful, for every vector x in the Right, because xi is a principal curvature vector, the orthogonal complement is invariant under the shape operator. The orthogonal complement is just the contact distribution. So we have also principal curvature vectors in the contact distribution. And if we choose such a principal curvature vector with corresponding principal curvature lambda, then this condition tells us that phi x or jx, well, actually I write now jx, is also a principal curvature vector with principal curvature 2 rho minus lambda. Yeah, on the contact distribution, j and phi is just the same. Again. We have a good expression for the mean curvature. The mean curvature is alpha plus 2 times n minus 1 times rho, which easily comes from the second condition. The fourth one is, and that's an important one, that rho is always constant. The fifth one, and that's something going to use later, for every vector x in the contact distribution, we have 2a squared minus 4 rho a plus 2 alpha rho. We apply this to x, and this can be written using the curvature tensor of the Kaehler manifold. It's r bar of jn n jx, and the orthogonal, and then taking the orthogonal projection onto the contact distribution. So this will give us some equations for principal curvatures. Then the principal curvature alpha is constant precisely if j of the normal vector is an eigenvector of the normal Jacobi operator everywhere. So this allows us to check the constancy of alpha using a simple curvature condition. And then I think this is what I just mentioned at the end of the last lecture. Or maybe I wrote this. Yeah, I think I actually wrote this. So the derivative of the mean curvature in direction of a vector in the contact distribution C is equal to the inner product between r bar of jn nn and jx. That's a simple expression for the derivative of the mean curvature in direction of the contact distribution. And what we get as a consequence of this, and I think this is what I mentioned at the end, that M has constant mean curvature precisely exactly this condition holds here. Jn is an eigenvector of Rn, so Jn is an eigenvector of the normal Jacobi operator everywhere. And I want to mention, I think that's a summary of everything, and I want to say something about the proof of 8. So this direction, when we assume that Jn is an eigenvector of, this is the other direction. this direction is quite elementary. So if the mean curvature is constant, then this holds. Why is this? If the mean curvature is constant, this vanishes. So this must be equal to 0. So this means that this expression here, r bar of jn and n, must be perpendicular to jx for each x in the contact distribution. So, but the contact distribution is j invariant, so this means that I get all vectors, I get the entire contact distribution here. So this one must be perpendicular to the contact distribution. It must also be perpendicular to n. There is only one direction remaining, jn. Yeah, so that implies that jn is an eigenvector. So if we do the converse, so if jn is an eigenvector of the normal Jacobi operator, this vanishes. So what we get from here is that the mean curvature is constant in direction of the contact distribution. So what we need is that it's also constant in direction of psi, and this I want to so this is easy. So why is this? Why is the converse true? So let's I think I want to denote by f the mean curvature. So then since this is 0 in direction of the contact distribution, the derivative of f must be just a multiple of eta, of the one form eta. Yeah, so we have df must be a multiple, so sigma, call this sigma, times eta. And sigma is just a smooth function on M. Yeah, so this is what we get from 7. Okay. So let's differentiate. We get 0 is d squared f, which is d sigma wedge eta plus sigma times d eta. But d eta we know is equal to 2 times rho times omega, because we have a contact hypersurface. So let's write down what this means. So this means that 0 is equal to we get d sigma x times eta of y minus d sigma of y eta of x plus 2 rho times sigma times, this is the fundamental 2 from g of phi x y. Yeah, so this is the equation we get from differentiating this. So now we replace y by phi y in this equation. What do we get? Phi y, so phi y is in the contact distribution, doesn't matter where we take it from, is in the contact distribution, so this vanishes. So we are left with minus d sigma phi y eta of x plus 2 rho sigma, and then we've got, I don't do anything here, phi x and then phi y. Okay. So in the next step we contract this equation. Yeah? So we sum over an orthonormal basis. So this one here, so we can assume that this orthonormal basis, that one of the vectors in the orthonormal basis is psi, and then the rest is in the contact distribution. So this here vanishes whenever the vector is in the contact distribution, so only the one with psi remains here, but then this is 0, so that's all 0. So we're left with these, but this is just like summing up orthonormal bases in the contact distribution, where we get 2n minus 2 vectors. Okay, so what we get is 0 is equal to 2 times rho times, and here we have a 2n minus 2. And I forgot the sigma. Now we know that, so this is all non-zero, rho is non-zero. So what we conclude from this is that sigma is equal to 0. Sigma is 0, this means that df is 0. So this tells us that f is constant. Okay. And when you actually listen carefully, you see I haven't actually used the fact that this is the mean curvature, constant mean curvature. In fact, this was a general result about when you have a function on a contact manifold, and this function is constant in direction of the contact distribution, then it must be constant on the manifold. Okay. So I want to talk about applications then. So the first one is, maybe it's interesting. Suppose, let's choose m bar n, a Kaehler manifold with constant holomorphic sectional curvature C. So then I think it basically was proved by Bochner long time ago. Such a manifold is covered by one of these complex space forms, complex hyperbolic, complex projective space, or complex Euclidean space. And one knows the curvature tensor explicitly for such a space. I don't want to write this down, but what one knows is always r bar n of jn is then c times jn. This is always true in a space of constant holomorphic sectional curvature, no matter which vector n you choose. So what we conclude from this is that, so we get as a corollary that every contact hypersurface in a Kaehler manifold with constant holomorphic sectional curvature must have constant mean curvature, and also the alpha must be constant. So every contact hypersurface in m bar n has constant mean curvature. So now I want maybe discuss the classification of contact hypersurfaces in complex Euclidean space. This is quite well known, this classification. I think Okumura established this, but it's quite a good illustration about how to apply these results to get a classification. So I want to discuss for a couple of minutes the case where the Kaehler manifold is complex Euclidean space. So M, and that is contact hypersurface. So what do we know? We know rho is constant, we know the mean curvature is constant, we also know that alpha is constant. Yeah, everything is constant. It's good. So then alpha and rho are constant. But then we also know more. Now we use this condition 5. Now when in the complex Euclidean space, this is 0. 0. So what do we get? Alpha is constant, rho is constant. So we get quadratic equation for the principal curvatures. The coefficients are constant, so the principal curvatures must be constant. Yeah. So from 7, we get that the principal curvatures of M are constant.
5.
What?
From 5.
Oh yes, thank you. From 5 we get that the constant. And since this is a space of constant curvature, this is equivalent to saying that this is an isoparametric hypersurface, and they were classified. Yeah? By Euclidean space, I think that's Segre in the 30s. So what are the so we use this result by Segre, we want to. So what do we know about M? So M must be well, let's just assume that must be an R2n minus 1, at least locally. I should maybe provide, must be an open part of this, but it doesn't really matter. So M is either Euclidean hyperplane, or M is equal to a sphere of some radius, or M is equal to a tube around RK in R2n, which we identify with the Cn. Yeah, so these are all isoparametric hypersurfaces. So if it's contact, it must be one of them. And then it's just what's remaining is to check, is the contact condition satisfied? Well, here this is totally geodesic, so this is 0, so that can't work because rho is non-zero. So this is not a contact hypersurface. The sphere that I gave as an example in the first lecture, we know this is contact. So the question remains, which of these tubes are contact hypersurfaces? Okay. So I draw a picture. We have RK. And then we have a tube. So let's say here our radius of the tube is R. So this is M. So this has always principal curvatures, and it has exactly two principal curvatures, and namely 0 and 1 over the radius. So if we choose the outward unit normal vector, so then what we get here, so we take the sphere here, And then from looking at the picture, you see where the principal curvature spaces are. The 0, so we get as principal curvatures. We get 0 and, well, this will be minus 1 over r because I choose the outward unit normal. And the corresponding principal curvature spaces, so the eigenspaces or principal curvature spaces. Basically, so this will be Rk, where I identify these spaces here in the usual way. And then here, this will just be the orthogonal complement of Rk and this normal vector. So if we denote this, this is our normal vector n. So it'll be, how do I write this? Maybe that'll be the R2n minus Rk plus Rn. So it's basically, that's the tangent space of this sphere here. Okay? So when is this? We have some necessary conditions. Let's check the first one. When is this actually a Hopf hypersurface? So what we want is that Jn is a principal curvature vector. Okay. So it must be either tangential to the Rk or tangential to the sphere for it to be Hopf. Yeah. So when is it Hopf? So M is Hopf precisely if for every, so normal vector, so we again is, so when it is tangential to sphere, means it's actually perpendicular to the Rk, or it is tangential to the Rk. So this means that the normal bundle, so what we need for this is that the normal bundle of I maps the normal bundle of Rk either into the normal bundle again, or into the tangent bundle of Rk. Yeah, so I maps the normal bundle of Rk, so this is my symbol for normal bundle, into the normal bundle or Rk or the tangent bundle of Rk. Yeah? So that's what one gets from this consideration. So when do we have the first condition? What does that mean? I maps normal bundle of Rk to normal bundle of Rk. That means that the normal bundle is complex, but then also the tangent bundle must be complex. So the Rk must in fact be a complex subspace. Yeah? So in this case, this tells us that Rk must be just some complex space Cl. So what does this tell us? So when does the normal space, when does I map normal space to tangent space? Well, then in this case, the Rk must be of the form I've gotten Cl plus some, and this is just the, that's then the I, well, IRK, no, that's not good. No, what should I write? Must be complex, normal, Rk, Cl. Maybe I should just write plus an Rm. It doesn't matter about the dimensions. It's just of this form. Yeah. So in this case, the normal space is mapped into this one. In fact, this is the same dimension, is it? Rk is mapped into... No, this should be the normal space. Okay, and then the normal space. Now this is right, just some Rm, so it must be of this form. So what do we get in this situation? When this here is a complex subspace. Then we get a zero subspace on a complex subspace. We look at this condition, and on this subspace we get zero here, so it can't be contact. Yeah? So we can exclude this case. So we are left with that one. So we're looking at this condition here. When is this satisfied? So in fact what we need here, again, if we get a complex part in the RK, we get 0 on this space. So that can't happen. So this one, if L is bigger than 0, we can get a contradiction. So the only thing remaining is really a half-dimensional real space. Yeah? So we must have L is equal to 0, so that the RK is just precisely the half-dimensional. So we must have M is equal to Rn. So what we have left, what we have got in the end is a sphere and an Rn. So if it's contact, it must be one of these spaces, and this is the classification. Yeah, so we have either a sphere or a tube around Rn. Sorry, not M is Rn. We must say M is tube around Rn. Yeah, and this is the classification of contact hypersurfaces in complex Euclidean space. Yeah, so one applies is a mixture of these conditions here. This is very useful, gives us a relation about principal curvatures, constancy, for example. Okay. And then you can guess that it's a similar method one can apply to get classifications in complex projective and complex hyperbolic space. So this was done by Okumura. So let me write for M equal to Cpn, Okumura in 1966, so that's a long time ago. And the classification looks pretty similar. What one gets is either geodesic hypersphere in complex projective space or a tube around a real projective space of half dimension. Yeah, so it's because the arguments are really is more or less the same as one did here in the Euclidean space. And for complex hyperbolic space, CHN this was done by Vernon in 1987. This needs a little bit some extra work, but what one gets is it's more or less the same. One gets distant spheres, tubes around real hyperbolic space of half dimension, but then also tubes around a complex hyperbolic hyperspace in here CHN-1 and horospheres, but that's all. Yeah? But the arguments are more or less the same. So I don't want to go through this in detail. So the next step is to investigate. That's what I'm really what I would like to find out is what are the contact hypersurfaces in Hermitian symmetric spaces. So M bar Hermitian symmetric space. HSS. And I want to assume it's difficult enough that the space is irreducible, but I don't. I consider both cases, the compact type and non-compact type. It sort of seems that the way one argues is more or less the same. And for complex projective and complex hyperbolic it worked, and there maybe it works as well. So Hermitian symmetric spaces, maybe talk about the compact case. We have complex Grassmannians, or the complex quadric. So that's an example. Or SO2n over UN, SPN over UN, and then there are these two exceptional ones, E6 over spin 10 times U1 and E7 over E6 times U1. So these are the compact ones. It's a short list really. So the questions are, maybe the first questions. Which is not obvious, but the answer is is here we saw that all the contact hypersurfaces, they have constant principal curvature, so especially they have constant mean curvature. Constant mean curvature seems to play a special role. Yeah, so my first question is, does every contact hypersurface in Hermitian symmetric space have constant mean curvature? All examples I know of have this property, but that doesn't mean that it's true. Yeah. And you see what it amounts to is one needs to study this condition here. Yeah, when is Jn an eigenvector of the Jacobi operator? Jn. Yeah, when we have a rank 1 symmetric space, so in the case when we have rank 1, so this is P is equal to 1, we have complex projective space, this is always true, because it's a space of constant holomorphic sectional curvature. But when the rank is bigger than 1, this condition is no longer satisfied. Yeah? In general, Jn is not an eigenvector of the normal Jacobi operator. And I tried to find out when this is the case, but it's not clear to me. So let me write down a proposition. So suppose M bar is a Hermitian symmetric space. We take a point in there and take a vector, a tangent vector, at that point. So then Jn is an eigenvector of the normal of this Jacobi operator. I'm not thinking about hypersurface at this stage, so it's just a question about Hermitian symmetric spaces. If and only if there exists a two-dimensional, totally geodesic, complex submanifold P of the Hermitian symmetric space, which contains the point O, and the tangent space of P at O is the complex span of n. So it's the span of Rn and Rjn. So, well, let me maybe first say why this is. This is not so difficult to see. So we can write m bar as g over k, and then look at the corresponding Cartan decomposition at the point O. So then the curvature tensor R of x, y, z can be written as can be expressed in terms of Lie brackets. So where x, y, and z are in P, which we identify with the tangent space of M. So the assumption here that Jn is an eigenvector of R bar n means that if we plug this in to this expression, Jn n is equal to somehow minus kappa Jn or kappa or whatever. Yeah. So that's the assumption. Now, since we are in a symmetric space, the existence of a totally geodesic submanifold tangent to some subspace of P the condition is that this is a Lie triple system. Yeah, so we have to look at all possible combinations of vectors in TOP if that actually is satisfied Lie triple condition. So the only other condition we need to check is the Jn condition. Yeah, that's the only remaining condition because there are just two tangent vectors, and everything else comes from curvature identities. Yeah, but it's minus R bar of n Jn. But since we have this is a Kaehler manifold, we can put J in front of the R bar. So that's a minus R bar of so J R bar of n Jn n. And also, since we have in a Kaehler manifold, we always have the property that R bar of xy is the same as R bar of jx jy. That's true in any Kaehler manifold. Yeah? So we can just plug in another j here. Yeah? So what we get is minus j of R bar of jn, j squared n, so this gives a plus n. And there we know, so what do we get? We had this minus kappa jn with another one, so we get kappa n. So that's fine. Yeah? So it's curvature identities from Kaehler manifold or so, which tell us that we have a Lie triple system. Yeah? So this tells us that Cn is a Lie triple system. So we have a totally geodesic submanifold tangent to it. So this is if this is satisfied, then we have the totally geodesic submanifold, and the converse is easy. So the question is, what are well, it's a two-dimensional totally geodesic complex submanifold. In the compact case, this must be a CP1 or a two-sphere. So it's a holomorphic two-sphere in there. And so the question is, and that I don't know, what are the totally geodesic holomorphic two-spheres in a Hermitian symmetric space? I'm not aware of a classification. Yeah, but that would figure out where actually this condition is satisfied. Yeah, so that's equivalent to this question. Yeah, so it's a question I have. I don't know the answer. What are the totally geodesic holomorphic two spheres in Hermitian symmetric spaces. So question: what are the totally geodesic holomorphic two spheres in compact Hermitian symmetric spaces, irreducible if you like? So to give you, I can solve this problem for two particular rank 2 Hermitian symmetric spaces. I did this just to see what comes out. So I know the answer for M bar is the complex two-plane Grassmannian or the complex quadric. The reason is that for both of these, there are very nice expressions for the Riemannian curvature tensor. One can do explicit calculations. Yeah? And the answer for these two spaces is, so it's a proposition, so proposition, so we have M bar is one of these spaces. Or the quadric, and N is a tangent vector, then Jn is an eigenvector of this if and only if N is a singular tangent vector of M bar. Now in higher rank symmetric spaces there is this concept of singular and regular tangent vectors. So every tangent vector to a symmetric space lies in a flat of this symmetric space, a maximal flat. A maximal flat totally geodesic submanifold. And generically this flat is unique. Yeah? But there are tangent vectors for which this maximal flat is not unique. These are singular tangent vectors. Yeah? And these are precisely the ones which for these two spaces satisfy the property that Jn is an eigenvector of R bar n everywhere. It somehow suggests that it's related to the singular tangent vectors in general, but still I can't prove it. So one can actually write this down in the case that when M bar is the complex two-plane Grassmannian, on the complex two-plane Grassmannian, we have the complex structure J, and we have the quaternionic Kaehler structure J. Yeah, that we have these two structures. So these vectors, this singularity condition is equivalent to saying that Jn is either contained in the three-dimensional space spanned by applying the almost Hermitian structures in J to n. That's a three-dimensional space, or Jn is perpendicular to Jn. Yeah. So then one can continue the game. So at least for the complex two-plane Grassmannian, so we know it must be a vector of this form one knows the curvature tensor explicitly, gets nice expressions, so then one gets equations for the principal curvatures. Yeah, so and then in this case here, one can show cannot be contact. So in fact only one case remains. Yeah, one can, using these necessary conditions, one can come up with a contradiction. So there's only one other case left. And so one uses this case, everything simplifies remarkably, yeah, in this situation. And one gets very nice equations, and what one then gets in this case is that n must be even. So n must be even, so n is equal to 2k, and m must be a tube around an HPK, quaternionic projective space, k-dimensional quaternionic projective space, embedded totally geodesically in G2C k plus 2. Yeah, and this is the only contact hypersurface in complex two-plane Grassmannian. So it's this was proved by Su in 2006. 2626. This is the only contact hypersurface under the assumption that this is an eigenvector, or equivalently, that the mean curvature is constant. Yeah? So this is the only contact hypersurface in G2C n plus 2 with constant mean curvature. But there is this question, I mean, is this a necessary condition, constant mean curvature? It would be nice to show. Now, since in Hermitian, in symmetric spaces, when you go from a compact to a non-compact dual, the curvature tensor just becomes the negative. Yeah? So all the equations are more, coming here into the picture, are more or less the same, except that here you get a minus sign. Yeah? So one can do the same, play the same game and get a classification, and it turns out in the non-compact dual also this cannot happen. It's only this case which can happen, of course, and what one gets here is just the dual situation plus a particular horosphere. It's a horosphere which has a point at the center at infinity, which is of singular type, of this type. Yeah, so the horosphere given by a geodesic for which the tangent vector is such a vector, and this proved in joint work with Dr. Lee and Professor Su recently. But again, the question remains of, do we have constant mean curvature? So, and I think, yeah, for the quadric, this is still work in progress. So one can actually identify explicitly the two types of singular tangent vectors and rule out one type, but it's not so clear. So that's still work in progress, and I think that's where I'd like to stop now. So thank you for your attention.